Howdy, Rex here. We're going to attempt to explain another thing you're going to have to be adjusting for at extreme long ranges, and that's Coriolis effect. That has to do with the spinning of the Earth underneath the projectile, which is in free flight above the Earth. This is something that you're not going to have to worry about if you're trying to hit a deer at 800 yards or whatever, but at extreme ranges, once you get over 1,000, especially if you're shooting at smaller targets, it will have a noticeable effect. Howdy, Rex here. What you're looking at is a Coriolis drift table generated for a 338 Lapua Magnum with 300 grain Sierra Match Kings. And we'll show you how to construct this after a little bit, but first we need to understand the concepts, and we have to understand what Coriolis drift really is. A lot of you probably know that it has to do with the spin of the Earth, and a bullet flying above the Earth, and the Earth is going to be spinning underneath it at different rates. So we'll explain that before we get into too much detail here. But as you'll notice, and you want to keep this in mind before we get into the explanation part, this table is broke up into a couple different temperature regimes. That's because your air density and your velocities are going to vary with different conditions. But within each of these different temperatures, you'll notice there's a vertical and a horizontal element to Coriolis effect. It will both affect your bullet's point of impact as far as up and down and left and right. Certain parts of it are respective to direction of fire, and other parts of it are respective to latitude. So what's going on here? Let's take a look. First thing to consider with Coriolis effect. The Earth is spinning, okay? It's spinning from the west to the east, okay? So this is the direction of motion right here. You can see on the arrows. That's why the sun rises in the morning. Actually, the sun is staying the same, but the Earth is spinning. So it appears to rise in the morning because you're spinning this way. If you were to look down on the North Pole, that would be a counterclockwise spin, okay? So we're racing towards the east at any given moment. The other thing to notice here is that the Earth is not spinning the same speed at every given spot on the surface of the Earth. Now the rotational speed will be the same because you're going to have one revolution per day anywhere you're standing, whether that be the equator or up near the pole. However, the actual speed at which you're spinning is going to vary. If you're at the pole up here, your rotational speed is the same. However, your actual speed is going to be pretty slow because it's not going to take a lot of speed to make it around the small distance. However, at the equator, you're going to have cover a lot more ground in the same time over a period of 24 hours. So the Earth is spinning way faster at the equator than it is at the pole. If you're right on the center of the North Pole right up here, it's not even hardly moving at all. You're just turning. So that's a very important concept to understand before we get started. Another thing to understand is just basic physics, and we'll mention this again later, but when an object is in motion, it tends to stay in motion until an external force pushes on it. So a bullet in flight is going to fly in a straight direction until an external force pushes on it. Which brings us to the definition of Coriolis Force, so-called, okay? Now, these definitions I got several of them, because this is kind of a hard concept to grasp. I want to give you guys some different angles. We're going to teach this from different perspectives, and hopefully it'll stick a little better that way. But I'm going to read you several different definitions. Coriolis force is an apparent force. It's not really truly a force. It's just apparent force. It appears like it's a force that must be included if Newton's laws of motion are to be used in a rotating system. First described by Gustav Coriolis back in the day, here 1800s, okay, in 1835. The force acts to the right of the direction of body of motion for counterclockwise rotation and to the left for clockwise rotation. On Earth, an object that moves along a north-south path or longitudinal line will be apparently deflected to the right in the northern hemisphere. and to the left in the southern hemisphere. The deflection is related to the motion of the object, the motion of the Earth, and latitude. So this is important not only for meteorology and oceanography stuff, but also in ballistics, okay? These other definitions do reinforce the idea that it's a hypothetical force. It's not truly a force. And also, you want to note that in the northern hemisphere, your deflected objects are going to always be to the right as far as your horizontal correction. And in the southern hemisphere, it's always going to be to the left. Okay? Let's get into a little more. We'll get into the math in a second here. But first, let's take a look at an overview of the different aspects of Coriolis in respect to ballistics. And then I'll take you out in the field and actually kind of explain it to you in a different way, and hopefully it'll make more sense after we explain this from several different angles, okay? So there's two different things you're going to have to be concerned with when you're doing extreme long-range precision shooting. We're talking 1,000 yards or more is when this really comes into play. Closer than 1,000 yards, Coriolis is not going to affect you enough to make a terrible miss. It will at 1,000, a good example, and it varies based on latitude, but horizontal correction due to Coriolis will just be on the order of 1 or 2 inches in a lot of cases. But let's take a look here. So you're going to have a horizontal Coriolis correction and a vertical, okay? Depending on which direction you're pointing, if they're vertical. Let's take a look at both of these. So this can affect your bullet both up and, up and down, and also from left to right. The horizontal Coriolis correction, okay, that's a deflection that is the same irrespective of the direction of fire. So your right and left Coriolis correction is not going to matter which direction your rifle is pointed on a compass, okay? In the northern hemisphere, it's always going to be to the right. In the southern hemisphere, it's always going to be to the left. That's the key things with horizontal Coriolis corrections, okay? It's always going to go to the right for all of us guys up here in the north. For you guys down under, it's going to turn you to the left, or appear to turn you to the left. The magnitude of the horizontal Coriolis correction is going to depend on your latitude, how far you are north and south. So if you're closer to the North Pole, for example, you're going to have a lot of horizontal deflection, okay? If you're on the equator, you're not going to have any deflection. And we'll illustrate this in a minute. So that's the main concepts to grasp as far as horizontal Coriolis correction. Northern hemisphere always to the right, southern hemisphere always to the left. At the poles, it's maximum. You're going to have a lot of deflection. And at the equator, and the closer you get, it's going to have less and less. And then once you get on the equator, it's going to have zero deflection. The second part of Coriolis corrections that you're going to have to be aware of is your vertical corrections. This is your deflection up and down. Now your vertical corrections are going to be changing respective to your direction of fire. So when you hear guys talk about having to adjust based on which direction they're pointed, they're talking about vertical corrections. That's going to bump you up or down in your firing solution, okay? So if you're shooting due north, your deflection is going to be 0. If you're shooting south, your deflection is also going to be 0. So if you're shooting due north or south, it's not going to affect your vertical deflection. Where it comes into play is shooting east and west. If you're shooting east, it's going to deflect your point of impact to be high. You're going to hit high, okay? If you're shooting west, it's going to bump you down just a little bit. It's going to be low. So you're going to have to crank up your scope to counteract for that a little bit, okay? The magnitude of your vertical corrections is also going to depend on latitude, just like your horizontal Coriolis correction did. And you're going to have 0 deflection at the poles and maximum deflection at the equator. So it's the inverse of the way this was, okay? Your horizontal, you had the most deflection at the poles. Your vertical, you have the least, or 0, okay? So this is probably right here a figure you're going to want to memorize, because this is an extremely important concept. There's no use adjusting for Coriolis force or apparent force. if you don't know which way it's going to go, or if you don't understand what's going on. So this right here, go ahead and pause that, copy it, do a screenshot. I'll also include this table in the description as well. This is extremely important right here to understand. Now, before I go back to the actual formulas, I'm going to take you out in the field real quick and explain to you what's going on, and then we'll come back and take a look at these and do the math, and then you can appreciate what's going on in the ballistic tables that we've generated for you. This is something that you're not going to have to worry about if you're trying to hit a deer at 800 yards or whatever, but at extreme ranges, once you get over 1,000, especially if you're shooting at smaller targets, it will have a noticeable effect because your target is going to be moving with the spin of the earth while your projectile remains in constant motion. If you remember Newton's laws of how stuff works, an object in motion tends to stay in motion. Unless an outside force pushes on it, that thing's just going to go in a straight line. So what you got to consider is that anytime you're standing on the planet Earth, the Earth is rotating. And it's going from the west towards the east. That's why the sun rises in the morning. And at any given time, let's say we're pointing north, for example, okay? That's north over there. See, take a look at beautiful north. Here where I'm standing in the south, that's the north over there. The Earth is spinning faster here because it's wider here than it is up there. If you think about the North Pole, in order to do a one rotation, it's a small distance it covers up real high north. You get towards the equator, and it's a larger distance that has to be covered in order to make a rotation. So the Earth is spinning faster towards the south than it is in the north. So if I set up a target over there at 1,500 meters or whatever, the Earth is not spinning as fast over there as it is where I'm at. So when I take a shot, firing due north, what's happening is, in addition to the forward velocity of the projectile going in the direction of the target, there's also going to be, the second that projectile leaves the muzzle, a certain sideways velocity. And that sideways velocity is going to match the speed of the rotation of the Earth where I'm standing. Okay, because if the Earth is rotating that way, which it is at a pretty good speed, there's going to be that sideways component to it. Now, as you get up there, the target is also moving to the right with us, and when that bullet's in free flight, there's going to be a difference between how fast the bullet's sideways component is and how fast the target is moving. So what's going to happen is, I'm going to shoot straight at the target, and the target isn't going to get there in time because it's moving slower than I was when that sideways component of the velocity was exerted. Okay? So what's going to happen is it's going to appear the bullet's going to hit to the right of the target. And it's going to appear to have veered off to the right, but what's happening is the bullet's remaining in constant motion and the target didn't get there quick enough because the Earth ain't rotating as fast up there as it is where I'm standing. Now, how much is that going to affect you? Not a whole lot. At 1,000 meters, it's going to be on the order of maybe about that much as far as your horizontal Coriolis effect. At 1,500 meters, it's going to be about this much. So it is something, if you're trying to shoot a real small target, you're going to want to adjust for that. And if you're trying to eliminate all your different variables and get as precise a firing solution as you can, you're going to account for all those different things. So, the Coriolis Force, or so-called Force, is going to make your bullet strike to the right of the target. Now, mind you, the bullet's going in a straight direction, but the target ain't getting there as fast. What about if you're, now this is northern hemisphere, we're talking, due to the shape of the Earth. It would be inversely so if we were in the southern hemisphere, because the Earth is tapering off in a different direction. If we're in the southern hemisphere, it'd be the exact opposite. So let's take a look over to the south here. So let's say I want to shoot south. So from our firing position here, way up in the north, the Earth isn't spinning as fast as it is in the south there towards the equator. Down there, the target's going to be going at a faster rate, going towards the east, than it is up here. So if I take a shot, there's a certain sideways component of the being exerted on the rifle bullet before it leaves the barrel, and that's not going to be as much as the target is moving down there, because the target's moving faster than I am. So what's going to happen is the target's going to get in front of the bullet, and the bullet's going to miss to the right. Just like we did shooting to the north, we're shooting south, and now the bullet still appears to be hitting to the right of the target. So your horizontal Coriolis correction, when you're shooting long-range rifles in the northern hemisphere, it's always going to deflect your point of impact to the right. So you're going to have to adjust left to counteract that. And an interesting thing to note is that it's actually true for your horizontal corrections. Any direction you're shooting, it doesn't matter if it's west or east, it's going to be the same amount of horizontal Coriolis correction, and it's going to be independent of direction. And the reason for that is the Earth is not a perfect flat surface that's moving uniformly. It's a sphere, and it's moving in kind of a weird way. You know, like we said down here, it's moving different in the curvature. It's going to actually, so the Coriolis force is always going to be to the right. So I can be shooting east or west, and your horizontal deflection is always going to be to the right in the northern hemisphere. Now, if you're in the southern hemisphere, your Coriolis deflection is going to be to the left, because, you know, the Earth is shaped like this. If you just visualize it, it'll be easy to comprehend. Another thing to note is that the amount of deflection is going to be dependent on your latitude, how far north and south you are. If you're towards the poles, you're going to have quite a noticeable effect. So we'll show you in the math portion of this video how to correct for that and calculate what your actual corrections will be. Now, if you're shooting due west or due east, there's another thing that's going to come into effect, and that's your vertical Coriolis adjustment. Now, unlike the horizontal Coriolis adjustment, like we just talked about before, that doesn't matter what direction you're pointing, but it does matter on your latitude. But your vertical correction, that's up and down, is going to matter based on direction. For example, if I'm shooting due west, you got to think about it. The second that bullet leaves the barrel, the Earth is spinning independent of the bullet, and the Earth is coming at us. So a target is going to be rising, coming over the horizon, and coming at us. So basically, your bullet is going to impact low, because the target is rising at the bullet and coming at you. So you're going to have to adjust opposite of that. You're going to have to come up because you hit low. Conversely, if we're shooting to the east, the second your bullet leaves the barrel, the Earth is spinning freely underneath it. The Earth is racing away from the bullet, and your target is slowly going low, behind the horizon and lower. So what's going to happen is you're going to strike high, so you're going to have to adjust opposite to correct for that as well. So as far as your vertical Coriolis corrections, adjusting up and down, it's going to depend on direction of fire and how directly you're shooting east or west. If you're shooting due north or due south, you're not going to have any vertical Coriolis correction. But you will always have a horizontal Coriolis correction independent of direction. So the two different components to get squared away in your head is your horizontal Coriolis effect, where you're going left and right. That's always going to be to the right in the northern hemisphere. It's always going to be to the left in the southern hemisphere as far as your deflection. And then you have your vertical Coriolis effect, which is going to be dependent on how far west or east you're pointing. All right. So here's the math behind the ballistic tables as far as Coriolis corrections. It's not too hard. There's a little bit of trig in here, but your horizontal deflections, that's how far left and right you're going to be deflected, is dependent on several things. You have the omega constant, which this is has to do with the rotational speed of the Earth, okay? And here's the constant. This is the value you put in for that, 0.0000729, and that's it goes on forever, but that'll get you pretty close. You're going to take your omega constant, multiply it by your range in feet squared. So however far you are, squared in feet, okay? So if you're, 100 yards, that's going to be 300 feet. Take 300 feet squared, or whatever. Now, 100 yards ain't going to have enough to have a horizontal deflection, but you get the idea. You're going to take that and times that by the sine of your latitude. What's sine? You got to have a scientific calculator here. And you're going to find the sine button there. So you're going to type in your latitude, and then you're going to hit the sine button. And that's what you're going to multiply it by. You're going to take all that, and then you're going to divide all that stuff by the average velocity. And that's something you're going to have to compute using a ballistic software. So this is not a correction you're going to just do in your head in the field, most likely. Like I said before, unless you're awesome. But I'm not that awesome to be able to figure that out. I like to just have it ready to go in some kind of ballistic table, okay? Your vertical deflection, you're going to notice that you have a little more complicated of a deal. This is kind of a gravity multiplier, and both these equations are not perfect because the shape of the Earth is not a perfect sphere, and everything doesn't work out linear like this. But basically, this will get you pretty close. And there's different ways to express this mathematically. But basically what you're going to have is you're going to also have your omega constant. That's taking into account your rotation of the Earth. You're going to have your muzzle velocity as a factor. And then you're going to have to figure out the cosine of your latitude. And then you're going to need the sine of the rads of the azimuth. Azimuth is the direction you're pointing. So that's the math behind it, and that can show some of the different relationships between some of these other factors. And that'll explain why when we look at our, let's bring up the Coriolis tables here. If you study those equations and then look at the results when we tweak our latitude, for example, okay? So let's, I think this is at 46 degrees latitude. That's about where I'm at here in the United States. Your latitude might vary based on where in the United States you're at, but you're going to have a pretty small deflection on your Coriolis. Now, that's another thing to note is your Coriolis deflection is pretty small, okay? And it's not going to be huge. And it's not even clickable. You got 10th milrad turrets, you're not going to be able to even apply a full click until you get out to 1,000 yards or so. Then you can round it up to a click, I suppose. But 1,200 is where you're going to have your first click, okay? That's just one click vertical correction, and your horizontal even at 1,000. So once you get to 1,000, it's a factor that you're going to want to adjust for. It'll be significant then. But 0 to 1,000 is not hardly adjustable unless you're shooting at a extremely small target. But let's tweak some of the things here. Let's change. Let's take note here. We got almost a click at 1,000 meters for both your vertical and horizontal Coriolis hold off at 46 degrees latitude on the Earth. Let's say we're at the North Pole. Let's go up into the table here, and I don't remember if you guys know how this works, but let's go to our latitude, and the North Pole is going to be 90 degrees latitude, right? If you remember your little geography class. Okay, so we changed it. Now we have a vertical correction of 0. Well, you're not really covering any ground enough to make an excuse to have a vertical correction. If you think about it, if you're on the North Pole, you're just spinning in a little circle like this. You're not covering any major ground. However, your rotational deflection is going to be quite a bit. So your horizontal is going to be the highest at the poles, okay? So that's why you have such a high horizontal correction is because, say you're on the equator, or let's say we're getting close to the equator. We don't have to necessarily max it out. Let's say we're like 3 degrees latitude, almost on the equator. Okay, now your horizontal corrections are very, very small, but your vertical corrections are big. So no matter where you're at on the face of the Earth, Coriolis drift is something you're going to have to correct for. If you're real close to the poles, which you're probably not going to be operating up there, there's nothing to shoot at up there, or down there for that matter. But basically, you're going to have to worry about one or the other. So you're going to have to understand the relationships like we showed you before. It's going to be very important, especially this page we showed you earlier. Have this figured out and have a good mental comprehension of what's going on. That way in the field you won't get all tripped up. And you'll just be able to look at your tables and you're not going to adjust in the wrong direction on accident, which is totally possible if you do not comprehend what's going on these tables right here. Okay, so study the tables, and it's going to be the exact same. If this is the first video you're watching, you're going to want to watch the video before this. I kind of introduce you to these ballistic tables and how to get set up with these on the spin drift video before this. And like I said before, I will release a video once this thing's fully operational, explaining in detail what's going on with this ballistic table setup here on Microsoft Excel. All right, so stay tuned. We got lots more coming up here. It should start speeding up after we get through all these real technical videos, and we'll start doing application of fire and marksmanship training and things like that. All right, let's get out of here.